the share the screen thing. No. Can you see it?
Not yet.
Oh,
There is nothing being shared.
nothing being shared. That's strange because it tells me that I'm sharing the screen.
Sometimes it takes a little while. So
Yeah, maybe it's that.
Okay, it's not privileges or anything like that, I assume.
What did I see here?
if you have problems, you can send a link and we can show here.
We just make a test here to see if you can see my screen.
Okay, shall I stop sharing?
No. So
something's coming up.
Okay, so
Yeah.
this is my screen, so it is working.
Yeah, I can see that.
Okay, so I will stop it. If you
Okay.
want to try again.
Shall I stop and try again?
Yeah, I think you should.
Okay. No?
No.
Huh. Oh, that's strange. Very strange. Just a second. Let's see if I can do something else here. Let's try again. Share screen. Still no?
No, nothing coming up.
Well, there are two possibilities. One
Yeah.
is for you to log off and come back in. Perhaps, something got
From the Zoom
yeah,
altogether?
get out of
Yeah.
Zoom and come back. And
Okay,
the other
let me.
option is to send us a link, and Rodrigo
Well,
could just.
yeah, I don't have it. I've just have it on my desktop.
Oh, I
I can
see.
email it to you. I can email it to you. I don't know how quickly it will get there. I'm sorry about that. Okay,
No.
let me first try that option of
Yeah,
I'll leave the Zoom.
and come back
Okay.
in. Yeah, okay.
Come back in.
Apologies to everybody.
Yeah. I'll leave.
Okay.
Hello again.
Okay.
And now let me see if I can share the.
Pronto,
Yeah.
yes, you got it.
Oh, good.
Yes.
Okay, so you're right. It was just some kind of. Okay, good. So you can see that, and I'll put it on a full screen. Now, is this a problem that we start late? Do I still have to finish
No, no
at the
problem.
top
No
of the
problem.
hour?
No problem.
Okay, I'll try to, keep it.
Okay.
Okay, so can you see the full screen?
Yes, we can see.
And also the
So,
cursor, if I point at the cursor,
yes.
yeah?
Yes,
Okay,
we can
very
see it.
good.
All right.
Okay,
So,
so please go ahead. Yeah.
okay, I'm going to do a short introduction. So, hello everyone. A very warm welcome to you all in this new talk in our webinar series. A kind reminder, this webinar is also being streamed live on YouTube. You can find the link on our website or access it on Linea's YouTube channel, Linea MCTI. Today we are delighted and honored to have Professor Ofer Lahav from the University College London. Professor Lahav is Parent Chair of Astronomy at UCL and is also co-director of the Center for Doctoral Training in Data Intensive Science, also at UCL. His research focus is on characterizing dark matter and dark energy from large galaxy surveys. He's also an expert in machine learning methods and AI within his research. And today he's talking about the aspects of machine learning for cosmological experiments. Professor Lahav, thank you very much for being so kind to accept giving us a webinar talk today on such an exciting topic. The floor is yours.
Thank you very much for invitation to talk to you, and good to see, some old friends and some new faces. Um, and as you've said, the talk, my own work and also the talk combines two disciplines. One is cosmology, the other one is machine learning, which is now very topical. But as you can see from the title, I'm going to take a somewhat critical view and asking, does machine learning provide us a revolution in our field, or is it just evolution? And we'll see also what other people think in the discussion. On this screen, you can see on the right-hand side, this is the Milky Way, and here is a footprint of the Dark Energy Survey, in which some of you are participating. And this is actually a dark matter map using weak lensing that the former student, Niall Jeffrey, has produced. And you can even see the unrelated, this is only for orientation, the Milky Way, and also large and small Magellanic Clouds. On the left is a modern version of the Starry Night. There's a famous Starry Night of Van Gogh. That's a modern version of it, which is actually now on display at the Van Gogh Museum. I happened to see it a couple of weeks ago. So, I don't know if there are enough dots here to justify it as being big data, but we certainly are facing that with billions of objects ahead. So I would like also, you very kindly introduced me, but I thought I'll just say few bullet points of where I'm coming from. That, you know, my current, I'm involved in those 4 projects. There's Euclid Rubin, but at different levels of involvement, and it changes, of course, with time. DESI has been my main activity over the past 20 years. But, you know, there's a question like, is dark energy just lambda, just cosmological constant? What is the neutrino mass? And that's coupled with machine learning, but also have some interest in history, sociology of the field, some activities on international activities on behalf of the faculty. And I'm based at University College London. That's where my position is. But as it happens, I'm talking to you from Oxford, where I'm a visiting professor. So the office you see with this beautiful red wall is not my office. I'm only a visitor here. And I'm also, as mentioned, co-directing the Center for Doctoral Training in Data Intensive Science. And I'll say a few words about it towards the end. I think especially Louise was interested in that. But these are 7 students of mine on that program. That those at the top already finished their thesis. Ben, Constantina, and Sunil, and the other 4, Prab, from left to right, Prab, Joshua, Paul, and Dakshish are working on it. And I'll show some examples from their work. So basically, this talk will have more or less 3 parts, 4 if you like. Just where we are with Galaxy servers. Of course, many of you are leading those projects, so you know all about it. But I'll just give a summary for the benefit of those who are not in the field. I understand it's a fairly diverse audience. And then I'll give some remarks. It already, while I was just connected, we had a lively discussion about the status of cold dark matter. And I'll even ask the question when to stop, where to go. And then we'll move to the AI, and I'll give a few examples along these lines of photos of explainability, anomalies, and even quantum computing. And then the training element, how do we prepare the next generation of astronomers to do data science? So this is really for the non-cosmologists on the line. We live in interesting times, not only in the world, but also in the universe. The universe is believed to have started 13.8 giga years ago, 13.8 billion years ago. And what we know is that it accelerated during inflation, but it's also accelerating now. And that's what we've kind of learned to appreciate now. It's nearly at least 25 years that we think that's the situation. Some people would say even more. And I think we seem to live in this paradigm that only 5% of the universe is made of ordinary matter, 25% or so cold dark matter, we still don't know what it is, and 70% this elusive dark energy. When I entered the field, we were told that it's only 5% ordinary and 95% cold dark matter. You don't believe me, the young people talk to Louise and Rogerio, and you know that was the mood at the time. So this was a paradigm shift, and I hope for a new paradigm shift. And that's, by the way, I recommend. This is the paper where Einstein talked about cosmological constant, 1917. It's in German, but there's a translation in the Princeton on the Princeton website. And this is, for those who have not seen it, this is the equation. You put cosmological constant lambda on the left for various reasons. One of them, he wanted a static universe. And then when the universe turned out to be not to be static, he thought it was the biggest mistake and it should be 0. He somewhat overlooked the fact it could have a different value. So now people think there is something like lambda, but the universe is not static, but rather accelerating, just different value. And there is a debate whether it's on the left-hand side, just like a constant of nature, like big G, or should it be on the right-hand side? There's some quantum fluctuations. Take the weak field limit. In addition to that, you have this linear term, and that's maybe for another lecture, but believe it or not, a linear term also appears in Newton's Principia. I repeat it, Newton's Principia. I'm not making a mistake here. So there is something there which is interesting. You can look up my website. We had a popular article about it. And, you know, it seems we have to learn to live with this lambda, however strange it is. And that's the driving force behind all these big projects. And this is a kind of pedagogical plot of densities against redshift. High redshift means earlier times. And if you do that and you define W as the ratio of pressure to density, C squared, you find that it evolves with the scale factor, which is 1 over the 1 plus redshift, with that power. And for example, for matter, it's just 0, so it's 10 to the minus 3. But for dark energy, if it's cosmological constant, if W is exactly -1, it's a constant all the times. So in the earlier times, matter was more important. But at some point, the universe started accelerating about 60 years ago. And later, now it's dark energy dominated. And we'll go through it, but current observations are consistent with -1 within 3%. That's a simple summary. Some may disagree because there's some deviations as well, but that's a short summary. And of course, these ideas, all these questions which go all the way from philosophical questions of what's the universe made of, and so on, and how old it is, and are there other universes, all these philosophical questions, luckily have been matched by huge effort by the community, thanks to the taxpayer. And there are projects like KIDS, Dark Energy Survey, DESI, which are of the order of $100 million, and then big things like Rubin and Euclid, that's $1 billion. And your groups in Brazil have been very active in this. And also at UCL, you know, some of the optics was done for both DES and DESI, the optical correctors, plus, of course, analysis, etc. And as many of you know, you're practitioners of that, we can use different techniques to learn about dark energy, dark matter. One of them is standard candles, the supernovae, that if there are different distances, we'll see them coming in different flux. Classes of galaxies, there are standard rulers, features such as the barometric acoustic oscillation, and reclensing, where objects get distorted by the intervening matter, and therefore we can learn about cosmological distances and the growth rate. So these four methods are very mature. We know their successes, we know their weaknesses, and that's a major activity now. So this is, of course, many of you on the line are members of Dark Energy Survey, a survey which started about 20 years ago. So it's also a comment that these things take a long time. And as you know, this is probably the largest sample, 1,500 supernovae. And you can see the results that appeared in January support W very close to -1 with about 3%. So this is the Hubble diagram. Yep, distance modulus again redshift. And these are all these supernova which were classified by their light curves. Now, this is the new kid on the block, so to speak. DESI, the spectroscopic survey, which already produced more spectra than ever collected previously. Now we have Luis da Costa on the line, who is really one of the pioneers of spectroscopic surveys, and he can tell you stories what it was like to measure one by one, to measure spectrum one by one. And here with these 5,000 fibers, we can measure all these tens of millions. Eventually, it will be a sample of about 35 million spectra of galaxies and LRG and ELG and Lyman alpha. And what happened here, using the first year of data, is that actually these features called barometric acoustic oscillations, which are essentially standard rulers, have been measured in seven different redshifts. Okay, so what I think is interesting, if you take simplest approach, Occam's razor, you'll find that just from DESI alone, W is very, very close to -1, let's say to within 15%. If you add other things, it's even, no, it's also even closer to -1, to within 3%. So, we got 3% from supernovae, we got 3% from here, we also got 3% when we did 3 times 2 point of DES. I don't know, they all seem to give this 3%, but it seems to agree with that. Of course, as you can see in the DESI papers, if you relax the assumptions and allow time variation in the form W0, WA, things can go wild and big error bars, and maybe there's some room. I take the view, it's all in the eyes of the beholder. We had a little chat just before we started. I take the view that it shows that it is consistent with lambda CDM. But of course, more data will shed some light on it. So I hope you're with me. I'm sort of trying still to give you just an overview, but also show you the amount of data that is growing and growing. And yeah, but still we see that. So we don't know, maybe we're all being fooled by systematics, although these are different techniques which have different systematics. Maybe it's just cosmological constant, maybe there's variation. There's a big question that is so big that it's not being discussed enough, that the particle physicists tell us it should be cosmological, the dark energy should be 120 orders of magnitude larger than that's what we measure. We don't know, and maybe there's some subsignature of modified gravity, maybe inhomogeneities, and maybe we can get more and more philosophical. Maybe just a multiverse where in one of those universes which have allowed life to evolve. And maybe the unknown, maybe future generations will laugh at us and say that what we've seen means something completely different, a bit like the epicycles. So who knows? However, lambda CDM seems to be a great success, but there are these issues where the double constant is 67, 73, this 5 sigma discrepancy. There is also discrepancy in the clumpiness of the universe, what's called the sigma 8 or S8, in the sense that weak lensing gives fluctuations which are smoother than what you expect from CMB. It's only by 2 sigma. There's some astrophysical explanations, maybe baryonic feedback. So, I mean, I want, for those who are not practitioners, you go to conferences, and what you hear is basically lambda CDM is doing pretty well, but there are few problems. And is it new physics or systematics? That's kind of the view, but maybe others may have different opinions. So you can take 2 views. One is we should work harder and harder until we go below the 3% errors to maybe 1%, maybe fraction of a percent. Or you say, okay, I know the answer and let's stop here, okay? So I know when to stop it's not a cynical remark. I think it's something that, in economics is a very big topic, right? You have to decide when to buy shares and when to sell shares. And there are many mathematical papers about it, on when to stop. And a kind of, 2 pages, if you like, Joe Silk and I have written in Nature Astronomy about this question, when to stop, right? And that's at any level. If you're a PhD student or you're a funding agency, you want to decide that. I personally think the short answer to that is, if there is a competing theory, it's very exciting to do more. But at the same time, it's also useful just to experiment, to do better and better and better. There's also a paper in a previous visit to Oxford. I collaborate with an economic historian, Avner Ofer, and we talked about, this paper is about the social value of dark energy. So it's for another discussion, but I'm just trying to give you a slightly bigger picture rather than just the technical one. So lots of data. Here it's only a subset of the projects I put just things closer to our heart. There's DESI, Rubin, Euclid, of course, SKA. You can see lots of data and how the number of galaxies goes toward the billions, and the cost goes towards a billion, and also number of scientists goes up. And these are two projects in which we've been involved, which use twin telescopes. One is the Blanco, and that's been used with a modern camera for DES, an imaging survey. And the other one is the Mail in Arizona. The Blanco is in Chile, they're in Arizona, to do spectroscopy. The first led by Fermilab, the other by LBL. And as I said, UCL built both optical correctors. And if you want to hear more, talk to Louise or Jerry and others. And also we produced a book. We suggested a book to document it, so you can look that up. And there's data are complete, as you know, but there's still weight analysis from the 6 years is still underway. And DESI is also doing extremely well, as I already mentioned, with half the survey already done. So I finally come to the AI. I just want to tell the context, So artificial intelligence is now being used everywhere. It's a big revolution now in many, many fields. I like to call it AI to say it's not artificial intelligence, but rather augmented intelligence. It's not my invention, but people have used it in literature, in the sense that I think we should combine it with human knowledge, not throw away human knowledge. I'll give some examples. And we want to combine it with laws of physics. So some people want it just as a completely black box that it will figure out everything. And I think it's more about connecting it to some laws of physics as well as to human knowledge. Now, we can think of AI as just as an extension of statistics. We've been dealt with data, since we're undergraduates, and we collected data in the lab and analyzed it and did regression and figure out whatever law of physics was under investigation. So it's really part of that, and I think we should, I phrase as questions, but I think we should really not look at it as black box. And when we get results, we should attempt to explain and interpret them, and to think how to minimize biases, because if you want to classify as cats and dogs, but you had too many dogs in a training set, you'll get a biased answer. So we want to think about that. There's a question, should you include physics as a prior, and also could you learn about physics? And I like this quote when I got interested in that long time ago, this quote that, only if you know how to make money without machine learning, you can also make even more with machine learning. So I want to give that impression, and also to connect it to well-known tools such as the Bayes theorem. Now, just a bit of reflections. I got interested in that in the early 90s, and we only used, this was our big data, 840 images from the APM machine in Cambridge, where I worked at the time. And we showed it to 6 gurus, among them the Vauquelin and Vandenberg, and other names, some of you know, John Hukra, and asked them to classify it on that T system that the Vauquelin invented, between -5 to 10. And then we published a paper in Science with all of them, all 6, and we showed that a very simple algorithm can reproduce it to about 2 types. So it's difficult to recover the 15, but you can do it within delta type of 2, which is, by the way, it's about the same as a scatter among humans, right? So this was fun, and we have extended it to the Galaxy Zoo later on, with Manda Banerjee and Chris Lintott, and so on. So I then, moved on to do other things such as dark energy survey, but then, of course, now it's a big explosion of that field, and I recommend to you this very nice review by these two authors that appeared a couple of years ago. And I think it's very, very nice. It's a bit kind of towards cosmology, extragalactic, and it talks about the applications for computer vision, galaxy properties, discovering cosmology. So there's many ideas there, which also talk about the success of different techniques. For those of you, some of you probably are practitioners of all that, but for those of you who are not, this is just a 30-second example of what machine learning does. So if you do supervised learning, and say you're trying to classify some objects, say flowers, you can measure properties of the flowers, say 10 different properties, the size of the leaves, the shape of the leaves, and so on, and you can make a catalog for those objects. And then you can train, because you know the answer for a subset, you can train it with 3 parameters that would say, if the size of the leaf is above something, it's that type of flower, say type A, and if it's larger, if it's slower, it's type B. And based on that training, you can fix those boundaries. Okay, so you'll have many, many criteria, set of numbers, and you do it, and then you show an unclassified, a new sample. So maybe you train it on 1,000 objects, and then you'll look at 1,000,000, and say you'll get then run it, and you'll find that it's class B, but you can run it again by slightly changing some parameters, and you'll get class A, and then you do it again, class A, and you can average them. It's like a committee. It's like you ask different votes on the committee, and then you declare that as the class. So this is like a 30-second summary. But of course, there are now many, many methods to do that. Maybe the thing to emphasize, again, with apologies to the expert, I'm saying things which everyone knows, but the old way of doing it, the way we did it in the early 90s, was to extract parameters in advance, say 10 or 20 parameters per galaxy, and show that, and then classify, like the example I just described with flowers. But what happened about 10 years ago, there was a kind of revolution that with advance of algorithms and computing power, that we can actually show the whole image. We don't have any more to extract, and that's called deep learning. So there's no pre-processing. My critical view of that is that the old method, I don't think, some people call it shallow. I don't think it's shallow at all, because it incorporates human knowledge, which is extremely valuable, right? So, for example, human knows that the background is sky, while this algorithm, which is deep, is actually not so deep. It's very mechanical. Okay, it doesn't know any physics. Nevertheless, deep learning has shown improvement on various things, and we work hard to get the data. Why not getting better results? And you can see the number of papers. This is the year, and number of papers with deep learning in the title grows up. And now to zoom in on our little corner at University College London. So we have this program, which I'll talk about at the end. And this is just a small subset of what's going on at UCL. This is work with students and postdocs who work with me. So it's a small subset, but you can see that, we've done work on photometric redshifts, on explainability of morphology, quantum enhanced classification, DESI spectra, entropy of spectra, causation, mass mapping, neutrino mass, mass of the Milky Way and Andromeda, and other things which are a bit remote from my actual expertise, things like supernova core collapse and trans-Neptunian objects. So lots of examples. I put this review article, you can see. So what I'll do in the rest of the talk, which I realized the limited time, I'll just go relatively quickly through some examples just to show you what it is. So It's not going to be in depth. It's all in papers and so on, but to give you a flavor. So photometric redshifts, that's an old problem that you measure. So this is a spectrum, same galaxy at 3 different redshifts, and you see it through filters. So obviously the amount of flux to each filter would be different, and you can use that to predict the redshift. When I first heard about it some 20 years ago, I thought it's a problem for one afternoon. What's the big deal? You take 5 numbers and you get out one. But as you see, the problem is still very much alive. It was quite central for the dark energy survey, and it's going to remain very central to the LSST-Rubin and Euclid. So more ideas are welcome. There are now dozens or so methods in the literature and so on. So at the time, we developed a machine learning technique, it's actually 20 years ago, where you put that in and you train on a neural network to get the redshift. You train based on galaxies for which you know the spectroscopic redshift, right? So you know the spectroscopic redshift. So you know the true answer. And then you show others, and it's working well, but of course with huge errors, and you have to do all kinds of tricks, especially if the training set is not representative. So the next thing, this was actually followed from a work by a group of Emmanuel Bertin and others in France, to say, why don't we show the whole image? Why extracting just 5 magnitudes? Let's show the whole image. And with a former student on that program, we have Ben Henges, who now works for an insurance company, by the way, because we prepare students for a dual career. So, but in his PhD, we looked at that, and indeed, if you show the whole image instead of just 5 magnitudes, you can improve by a factor of 2 in terms of RMS. So it doesn't change the world, but it does improve things by a factor of 2. This is another question which is kind of fun. This is with another CDT student called Prab Bambra and my colleague Benjamin Yokimi. Is the question about what is it in the galaxy image that you decide to call a bar or a bulb. So here we're taking the sample of images collected by the Galaxy Zoo team, and so if you like, many human brains looked at that image, the galaxy, okay, and they, for example, decide to call it bar, okay. So we can do an exercise. This is from the literature. It's a technique called smooth grad, where you take derivatives of the output with respect to the input, and you do what's called a saliency map or a heat map, sensitivity map. It shows you what part of the image caused the human brain to say it's a bar. And it does a pretty good job, and you can even do a measurement on that sensitivity map, which is the axes are very small, but it's the y-axis compared with measurement by human, in this case Ben Hoyle, and you can see there is a good correlation. So you can think about automating that whole process. But it's kind of fun to really see what is it that tells you something as a bar or a spiral arm, etc. You might have heard about quantum computing. I'm an absolute beginner in that, but luckily at UCL I have several colleagues from particle physics who have started it. And while in the classical computing we have 0 or 1, here we can have a qubit which can take any value. So it gives you more flexibility in a way, more nonlinearity. And that's what happened here. So, we tried a very simple problem, ellipticals and spirals. I don't know if it's good news or bad news, but the quantum computing does just as well as the classical technique. In this case, we use support vector machine. So at the moment, this quantum computing hasn't improved But also, it has to be said, we gave it a very, very easy problem of only 2 classes, where I told you that 30 years ago, we already had 15 classes. So we just have to do more work on that. And it's like another new kid on the block, which is worth exploring. Moving from images to spectra, I mentioned to you we have this tens of millions of DESI spectra now, and we have access to it because we are one of the institutions involved in DESI. And this is the question really of characterizing spectrum. This is an elliptical galaxy. You can see quite an impressive spectrum from DESI. This is, as I mentioned, there are 5,000 fibers. So this is, what you get to one of the fibers. And this is a result of PhD of Konstantina, who finished her thesis with me in that program. And what she's done here, variational autoencoder, I don't have time to go into it, but if you like, you can think of it as an extended version of principal component analysis. You take the data and compress it into lower dimensionality and then reconstruct it. In this case, here 10, it's a sample of thousands of beams in the spectrum being compressed by a factor of 100. So blue is the original spectrum and black is the reconstruction. And you can still see quite nicely all these lines. And then we thought in that program, the students spent 6 months working in industry. So Konstantina worked with me on various other problems, including gravitational waves and so on. And then she went to work for a company in London, and she worked on anomalies. And the purpose of that was for fraud detection, okay? If your credit card is stolen, you get, and someone is trying to use it, you get an alert from the bank. Why? Because they've seen an anomaly, right? Because suddenly someone is trying to use a big sum. By the way, it just happened to me recently in a visit to Paris. My wallet was stolen and I got a call from the bank. So there was an AI algorithm there that said, oh, this is a fraud case. So when she came back, Konstantina, we said, why don't we use it actually sorry, I'll skip that one, I'll move to that one. We said, why don't we actually use it to look for anomalous spectra in DESI? And now, fortunately, Konstantina stayed in the same company to do other exciting projects for this community, for society. But I have a new student called Paul Nathan, and we're now working on this, of course, with some other collaborators. And the point is, you can take, for example, these 4 spectra, and this one is all normal when you reconstruct. This is, by the way, the autoencoder. You compress it from many, many parameters to 2, let's say. You have 2 dimensions, and then you expand it again, and you see how it will reconstruct and some criteria. But you can see, for example, this one is clearly an anomaly there. And what this method finds is either you find problems, for example, with the redshift. If the redshift is wrong, you get this anomaly, or it could also be something more interesting. For instance, a supernova, say, explodes in a galaxy, and the spectrum is superposition of the galaxy and the supernova spectrum. So we hope to turn it into some kind of pipeline activity, and that's the story, basically. Before I close, I'm almost there, but before I close, just to say that we focused on galaxies, images, and spectra, but there are many other applications. For example, we have a group at UCL that builds a satellite called Ariel. The PI is my colleague Giovanna Tinetti. And what they have done, colleagues Gordon Yip and Igor Waldman, they're basically looking, this whole purpose would be here's a star and you see a spectrum of the star, But if there's a planet going through, then the atmosphere of that planet would create a different spectrum, and this could tell you then about all kinds of lines in the atmosphere. And it's going to be very exciting. It will be launched in 2029. But what we've done now is some sort of data challenge to do that. By the way, it's public if you want to participate in this data challenge, which attracts also computer scientists and others. So I hope you get the idea that just the way we think about unusual galaxies, they can also think about unusual spectra, which could tell you maybe about life. Okay, so all this AI is very broad there. So there are all kinds of open issues about how to represent the spectrum. Would machine learning really improve previous approaches? How sensitive it is to spectral coverage and so on. All kinds of techniques. I very quickly went through. This is a slide which goes back to a paper we did a long time ago, now being revisited with Ignacio Ferreira to look at the spectrum, to ask about the information content, okay? How much information there is. So these are ideas from information theory. You probably know about the Kullback-Leibler divergence, and it can tell you about the spectrum relative to the class. So, to what extent a galaxy is represented by the mean of its own of its class. Okay, now especially Louise asked me to. So am I okay to speak for another 3 minutes or so?
Sure, no problem.
Yeah, okay, I'm
Go
nearly
ahead.
there. But Louise has asked me to tell you a bit about this program we have at UCL. So this started about 7 years ago. In fact, it was an initiative by the Research Council. They could see that this AI revolution is coming. And they said, create a system that prepares students, PhD students, for dual careers. Not everyone would become an astronomer, but there's great need for data science. And we were lucky to get the grant for this, and also second time. So we're on phase 2 of this. And so this is this program called the PhD program. And we also have, I'll say a few more words about it. We also have an MSc program for 1 year. We have about 30 industry partners. Like I mentioned, that 2 students who work now in companies. So we have 30 of those. We have international activities, which we wish to expand, and I'm happy to discuss it with some of you, if there's interest in Brazil in that. And of course, research and all kinds of activities. For example, this group I described that has done is looking for spectra of exoplanets. They just had a hackathon, which everyone can join, and they do this grand challenge. Who would be able to detect what? So lots is going on, and some of it is open. You can join us remotely if you like to some of the talks, and of course you're welcome to visit. And I'll be very happy to follow up this presentation by other discussions. And this is specifically that center. It's now 75 students have been through it. About 30 have already finished. They submitted, defended, and there are over 190 or so publications. The program is such that it's for 4 years, yeah, and 3.5 years is spent on the actual blue sky topic, whether it's astronomy or particle physics. But the students also spend 6 months in a company. So I mentioned Constantino spent 6 months in a company to do anomalies for fraud detection. And incidentally, they employed her straight away. So after she worked there for 6 months, they liked her work, and they gave her a job. So it's really quite amazing, this connection with the industry. So this is our triangle, right? We have the students. They're, of course, the most important people in this game. And we have the industry partners, about 30 of them, and it really covers, one of them is ASOS, that's fashion retail. Another one is an oil company. Another one is the nuclear fusion. Also, magazines, for example, The Guardian is a partner. So students, they also do, by the way, a small project on the first year, a group project. So some of them have done a project with The Guardian to analyze articles, to look for particular pattern on how politicians talk about racism, right? So you can do analysis of certain words that appear and so on in the context and compare it today to 30 years ago, 60 years ago, and so on. And of course, we're all plugged into this big project, like we are collaborators with you on some of them, such as DESI, LSST, and so on. So it's a very nice way of bringing together different disciplines. And as to the question I posed, is it an evolution or evolution? I think there's a lot of pipeline, great. I think we're still waiting maybe for a killer application. So I asked ChatGPT that question. Is deep machine learning for cosmology an evolution or revolution? And ChatGPT is very diplomatic. So you can see I emphasize in red, it says deep machine learning has the potential to fundamentally change the way that cosmologists approach and study the universe. So, it's quite diplomatic. But in any case, this is my last slide. I'll just summarize. I think it's quite amazing. We have huge data sets. And it's not only a special domain, of course, time domain. I think it's fair to say that cosmology can no longer be done without machine learning. With these data sets of LSST, Euclid, etc., SKA, of course, we can no longer think about doing it without. However, if I want to take a critical view, I think we're still missing a killer application. You might have heard about the success a company called DeepMind has done, this work with protein folding, and also they also had algorithms to discover new materials. Hundreds of thousands of new materials without having to go to the lab. That's really great, and I feel in astronomy we're still missing something, which is a complete game changer. That's my humble opinion. And in terms of challenges, really this deep versus shallow, how to understand, interpret results, how to incorporate physics or learn physics, how to upscale algorithms. There's the whole issue of ethics, which is quite important. If you work with companies, it's about, what is it going to be used for? And finally, as I said, it's a great playground to train students and postdocs beyond academia. So this is it. This is completes the lecture, and thanks very much for listening.
Okay. Thank you, Professor Lahav, for the very exciting talk. Now we have time for questions from the audience. If you
So I'll
joined
stop
us,
sharing, I think, so I
okay.
can see you.
If you have questions, if you are with us here in Zoom, please raise your hand and ask your questions. And if you joined us on YouTube, you can put your questions in the comment section. So questions?
Yeah, I can see a hand up.
Yep. Okay, go ahead. I think I may have some problems here.
Okay.
I
So
think it's Julio has the question.
Okay.
And then Luan.
Professor Lahav, thanks for the excellent presentation. I'm really not an absolute, not specialist in artificial intelligence. So I'll try to put a question as simple as possible. also in the hope that I will have the answer the answer for the thing for the question I really want to know. About the true use or the true capabilities of artificial intelligence, it's just only a matter of going faster or knowing better what we already know. For instance, having more having the consequences of what we know without having any creativity beyond that, or it's really the possibility of having something new, new ideas or new concepts, or a real better understanding of about the universe beyond the theories we already know, we already have.
Yeah, that's of course a valid question, and I alluded to it. I think it's a mixture of both. So I think some of it is pipeline. Okay, I mean, if you want with photometric redshifts, it's really just more about actually getting whatever redshifts for a billion objects. You just want to do it. But I think far more exciting is what you said, which is a new discovery potential, right? That there'll be something there. So, for instance, you can ask the question, would machine learning, could it have discovered the pulsars, okay, which was, as you know, discovered by a human, just in Brunel Bell. But maybe if you think about something similar, a big survey, and a machine could detect maybe some regularity of the signal, and there'll be a lot of that with LSST, a lot of time domain. Then I think this could be really that, pulsars, it was a sort of Nobel Prize discovery, right? So you can imagine there would be something like that of discovering unusual objects, what I call anomalies. That's one way. There's a whole area of a growing area, which is interesting, called symbolic regression, that you give data and the algorithm actually figures out equations, right? It discovers laws of nature, right? You give it data points about the solar system, about planets, and it comes back with Kepler's law. So that's pretty nice. So who knows? Maybe it will go that way, that we really discover new laws of physics. Yeah.
Got it. Thanks.
Luan, go ahead.
Okay, thank you. Thank you very much for this amazing lecture, Professor. I'd like to ask about in the realm of cosmology. We know that usually we are using a lot of data science techniques and also artificial intelligence to classify and forecast data in astrophysics. But I would like to know, what do you think about we can use machine learning, deep learning to constrain new dark energy models or alternative models from the realm of cosmology, and how we can do that using this new type of data or data augmentation? So I'd like to.
Yeah, it's a good question, somewhat related to the previous one. I mean, it goes to different levels. Of course, it's one can think about in many directions, but here are a few directions. One is maybe it could help us to understand systematics, right? So there's something wrong with the redshifts or with the way we analyze the data. That's one thing. It's kind of to diagnose the data. So that's because maybe just systematics that make us think that it's new molecular gravity. That's one. The second one is the sort of thing I talked about, which is to present an algorithm data and let the algorithm discover something new, right? So maybe you look at the residuals, you look at it relative to your standard model, and there's some delta, which is a deviation, and maybe you feed that delta into symbolic regression algorithm, and it would come back and say, wow, here is, a new term in the whatever the equation for bending of the light, and Einstein was not quite right, and this would be very, very exciting, you know. But we'll see. There's a third area which I haven't talked about, so it's an opportunity to say one sentence. It's called emulation. So as you know, in this service, we need big simulations, but they're expensive. So the idea is, there are many papers about it now. The idea is you can produce some expensive simulations, but a small number of them. Let's say you use 100 expensive simulations, but then you can take cheap simulations, which are done by a simpler method, and teach the cheap simulations based on the expensive simulation. You follow what I'm saying? So there's some kind of learning process. So it's called emulators for historical reasons. So that's, again, it's a tool. It's not by itself a discovery, but it's an interesting tool where it could help you and save lots of computational time. Yeah. So it's a whole range from, if you like, mundane tasks to really things which are, you know, very more inspiring and in the discovery domain. Thank you. Yeah.
Thank you very much.
Thank you. Luis?
Hi, Ofer.
Hi,
Well,
Luis.
as always, a very impressive talk covering so many topics. I have a very quick question. I mean, how can we find ways of plugging in Brazilian students in these courses or this program, which is so interesting? I don't think that the local industry has the maturity of doing that, but it would be nice to have some way that we could plug in the Brazilian students. Can you see a way of doing that? Because I saw that there was an international something.
That's
there.
right. That's right. No, it's very timely, Luis, that you're asking that question. Very timely. So I'll tell you a couple of ideas, and I'm sure I'm very happy to follow it up offline in coming weeks. One is, of course, individuals can apply to our program, right? So if you have, you know, MSc students, master students, or undergraduates who want to do a PhD in London, then can apply. Of course, it's competitive. We get what we had 130 applications for 12 places. No, for 9 places. So you can see it's a factor of 10 oversubscribed.
Yeah, it's pretty.
But you have many bright people. I've seen them coming over the years through DES and so on. So one possibility is for individuals to apply and come to UCL. I see some people on the line who are ex-UCL, like Bruno, so they can tell you all about life in UCL. And that's one direction, okay? Another direction is, you know, if people were happy, well, we're actually changing a bit the format of seminars. So I have to check, because it used to be seminars like this, but it's now part of more of a tea time meeting, which the students organize, which is a bit less formal. So I have to check what would be in terms of the, you know, doing things online. But that's another possibility. If we have an event which is online, if individuals like to join, you know, we're very happy to add you to an emailing list.
Mm-hmm.
And
That would be
some of the
interesting.
talks are by people from industry, for example, and you know, time difference is not too bad, 4 hours or so. So, you know, this can also work. The third one is more ambitious. I'm actually in the process. I showed you this umbrella called DESI. And what I'd like to do, I'm sharing with you openly some aspirations. I'd like us to create an international network of, you know, maybe initially 5, 6 institutions, and I'm already discussing it with some, to have a cooperation, you know, not in any bureaucratic way, but for example, if there are calls for exchange schemes, right? There's money there. It's just that you need to know to apply by given time to a right scheme, and a student can come for 6 months, let's say, if such a thing exists, and participate in some of these activities, right? So
I
I'm
think
very
we
happy
should
to.
talk, I think we should talk about that because I was actually looking at the other day. There are a lot of bilateral agreements between CNPq and the STFC, and I think we should explore that.
And sometimes there's money there, and as you say, exchange all kind of schemes, but you just need to know that they exist.
Yeah.
I actually had a project with Jordan.
I know. I remember we met when you were flying to Jordan.
That's an interesting story. But that's an example that the UK has some or had, now they stopped it COVID, some agreements with about a dozen or so countries. I cannot remember now if Brazil is on that list, but maybe it's on another list. They have all kinds of schemes. So I'm very happy, Luis, to explore that.
Okay,
and I would like on time scale of months to set up. I just exchanged an email the other day with another group to maybe define some kind of network and use either existing resources, just to use them wisely, or to also apply for new grants if there are some opportunities. I think it's very exciting, and it's also possible to do things online.
That's right. I mean, nowadays it's really possible to actually
it's not such a big deal. It's not different than doing DESI.
That's right.
Or LSST. I mean, it's the same thing. It's just you create a different umbrella there. Yeah. Good.
Fantastic.
I'm glad you're interested. Yeah.
I continue to be interested.
Yeah.
Thank you very much for coming.
Yeah, pleasure.
Okay. Thank you, Luis. Do we have any last questions? Okay. If there are no more questions, we will now wrap this up. This presentation will be available on our website and on Linus' YouTube channel. Thank you, everyone, for attending, and a special thanks to Professor Lahav. And
thank you very much.
Okay, everyone have a great day. Stay safe, and I hope to see you all again in our next webinar. Thank you.
Thank you. Bye-bye.